Depth first search. So many interesting computational problems are easier to solve if we model them using graphs. Now when we use graphs in an algorithm, we need a way to represent the graph. So the most simple representation is what is called an adjacency matrix. An adjacency matrix is a square matrix where the rows and the columns correspond to the vertices in the graph. And the entries are usually 0 or 1. And an entry is 1 if and only if the corresponding pair VW actually denotes an edge in the graph. Now if a graph has very few edges, then most entries in the adjacency matrix are 0, and it's inefficient to scan a row of the matrix to determine the neighbors of a vertex. In such situations, we typically use an adjacency list. With each vertex V, we associate a list L of V, which just lists out the neighbors of the vertex V. So here is a graph with 10 vertices labeled A, B, C, D up to J. The adjacency matrix for this graph would be as follows. So we'll have a 10 by 10 matrix labeled by the vertices. In this matrix, we have only labeled the ones. The zeros have been left out and left blank to avoid cluttering up the matrix. So for instance, we see that DC is 1 because there is an edge from D to C. But DB, for instance, is blank, that is 0, because there is no edge from D to B. So on the other hand, here is the adjacency list representation of the same graph. So for each vertex, we have a list of vertices which are connected to that vertex by an edge. So A is connected to C, D, and E, B is connected to E and F, and so on. So look at this graph. So each vertex has either 2 or 3 neighbors, and it's pretty clear that in such situations the adjacency list is actually much more compact than the adjacency matrix, in which most of the entries are actually 0. So given such a representation either as an adjacency matrix or as an adjacency list, we need a systematic way to explore the vertices in a graph. So one such strategy to systematically explore a graph is called depth first search. Depth first search, we proceed as follows. We start from some vertex V, and then we look at all the neighbors of V. Now we may have already seen some neighbors of V because of some earlier exploration. So for those vertices which are neighbors of V which are not explored, we recursively explore the graph from that vertex using exactly the same procedure. The reason that this is called depth first is because we start with one neighbor and we recursively explore it as far as possible before we move to the next neighbor. So we shall see an example of how this works on the graph that we have seen before. So let's see how depth first search works for the graph that we have seen before. In general, we'll start with vertices in the alphabetical order of their name. So we begin with A. So we start with A and we mark A as visited. Now A has 3 neighbors, C, D, and E, none of them which are visited. So we take the lowest of these, which is C, and visit it next. So we mark C as visited. Now before we go back to D and E, we have to look at the neighbors of C itself. So C has 3 neighbors, A, D, and F, of which A is visited, so we skip it, and we go to the first unvisited neighbor, namely D. So then we mark D as visited, and now we have to look at neighbors of D. So if we look at neighbors of D, we find that it has only A and C, so we can't visit any new neighbors from D. So we go back to C and explore its next unvisited neighbor, which is F. So we mark F as visited. And now we have to explore the neighbors of F. So F has neighbors B, C, and E. So B is the first such neighbor in alphabetical order, and it is not visited. So we mark it as visited and add it to our exploration. Now we have to visit neighbors of B. So B has 2 neighbors, E and F. E is not yet visited. So we mark E as visited and come here. Now we go to E. Now E has 3 neighbors, A, B, and F. All are visited. So we get out of E and come back to B. B has no more unvisited neighbors, so we go back to F. F has no more unvisited neighbors, so we go back to C. C has no more unvisited neighbors, so we go back to A. And now A, we started with C, and we had 2 more neighbors, D and E, but both of them have already been visited when we were processing C. So A has no more unvisited neighbors, and so we have to stop exploring from A. At this point, we go back to the overall set of vertices and find the first vertex which is not yet explored, namely G. So we start another version of our exploration starting at G, which is a separate part of this thing. So G tells us that it has two neighbors H and G. So we mark G as visited and we go to its lower neighbor, which is H. Then from H we go to its unvisited neighbors, which is I. And from I we go to its unvisited neighbor, which is J. And now we see, of course, that everything is marked, but technically J has no unvisited neighbors, so we go back to I. I has no unvisited neighbors, so we go back to J. H has no unvisited neighbors, so we go back to G. And now G also has no unvisited neighbors, so we exit from G. Now we observe there are no more unmarked vertices, so our overall depth first search exploration is complete. So we can now examine this structure that we have built up. So you can see that we have a tree starting at A and another tree starting at G. So in general, this is what we call a DFS forest. A forest is a collection of trees. So DFS produces a collection of trees, one for each connected set of vertices in the graph. The other thing that we can do in this tree is to actually mark the edges we did not explore because they were to visited neighbors which we had already seen. So we went from A to C, then we went from C to D. Now at D we deliberately didn't explore the edge to A because we had already visited A, but there is such an edge, so let's put it in green. So this is an edge which is not in the tree but which is in the graph, and we'll draw it in a different color. Now when we come from C to F, and we go from F to B, okay, and then go from B to E. Now E, again there is an edge from E to A which we did not explore because at this point we had already visited A. Right? So all edges which are in the graph but which are not in the DFS forest will be marked in green. Now in this outer rectangle, the edges that we have are 1 to G and 1 to I. From I we have H and J, and at J we do have an edge which points to G, and this edge was not explored because G was already visited. So in the terminology of DFS, the blue edges, the tree edges, are those which are explored while going forward, and the edges that you ignore are called back edges. Right? So back edges are those edges which are present in the graph but are not explored by the tree. The other thing that we can actually do when we are doing DFS is to see the order in which we enter and exit. Right? So initially we enter 1, A, then we enter C as 2, then we enter D as 3, then we finish processing D. So we have a different number saying that we finished D, then we go back to C, we haven't finished C, so we enter F. So F is the 4th vertex we enter, then B is the 5th vertex we enter, C is the 6th vertex we enter. Now we finish E. So now this is the 2nd vertex we have finished because we had only finished D so far. Then we go back to B, there's nothing further to do with B, so B is now the 3rd vertex we finish, right, or exit from. And then we come back to F. F has no further thing, so we exit from F. So F was entered number 4 and it also exited number 4. Then we come back to C. C has no further vertices, so we exit. Then we exit. And so after 6 steps we have numbered these. So black are the entry numbers. This is the order in which we entered the vertex to explore. The red numbers are the ones in which we exited the vertex after finishing exploring all its valid neighbors. Then we come to the other side and we can continue our numbering. So we enter G as step 7, we enter H at step 8, we enter I at step 9, and we enter J at step 10. And then we finish processing J, so that is the 7th vertex to finish. I is now the 8th vertex to finish, H is the 9th vertex to finish, and G is the 10th vertex to finish. So there are several things therefore that go along with DFS. One is the structure of this DFS forest, which has tree edges and the missing edges which we call back edges. And the second thing is the sequence in which we enter and exit. So one way of thinking of entering and exiting is that every time we suspend process, so we go to A and then we suspend processing of A in order to process its first neighbor C, we are putting A on a stack, okay, implicitly. Then we suspend C and go into D, we put D on a stack. When we finish D, we pop D off the stack, so the stack now goes back to A and C. Then we push F on the stack, then we push B on the stack, then we push E on the stack, then we pop E, B, F, pop C, pop A, now the stack is empty. we again now push G on the stack, push H on the stack, push I on the stack, push J on the stack, and then pop them back in reverse order. So that's what these numbers are reflecting, the orders in which we push and pop elements from the DFS during the DFS onto the stack and pop them off the stack. So if you look at the DFS forest that we constructed, every back edge leads back to an ancestor in the tree. So the edge from D to A is from D to an ancestor A. The edge from E to A is also from E to an ancestor A. From J to G is also. So the question is it possible to have edges which are not to an ancestor? For example, could there have been an edge which we did not explore which takes us from F to D or from B to D? So is it possible to have a back edge that is an edge which is not in the DFS tree, which does not take you back to an ancestor within the DFS tree? So the answer is that this is not possible. And the reason is simple. So supposing there was an edge from D to F, then when we were exploring the neighbors of D, since D was explored before F, at that point F would have been an unvisited neighbor. So F would have been added below D. We would not have had to go back up to C in order to explore F. Right? So it turns out that the only edges that we can ignore are the ones which are already explored implicitly above us. So there cannot be any back edges which go across the tree. They can only go from a node or a vertex to one of its ancestors. So here is a formal description of the DFS algorithm. So we actually have two levels. We have capital DFS, which is the algorithm for the whole graph, and we have a function small DFS which explores the graph from a given vertex. So what we do is we keep track of which vertices have been visited using an array called mark. So initially we say that all vertices are unmarked. So we initialize mark V to be 0. Now we are going to be keeping track of the order in which we enter vertices as part of this marking procedure. It's enough actually to mark things as yes or no, but we will actually add more information and keep track of this sequence. So we keep a global variable called count, which is going to count the order in which we enter vertices in our DFS. So we initialize count to 0. So now what we do is we run through our vertices at the top level in our graph, and we pick the first vertex we find which has not been marked, and we initiate a DFS from that vertex. So when we initiate a DFS, we come to this function. So the first thing we do is we increment the count, and we mark this vertex with its entry number. So the entry number of this vertex is the new count. Now for every edge BW, that is every outgoing edge from V, we check if W has already been marked. In other words, if it has a non-zero mark. If it has a 0 mark, it has not been visited so far, and so we then recursively explore from W, and eventually when we finish exploring all the edges outgoing from B, we will return from B. So this is a straightforward recursive implementation of DFS. Notice that the stack that we mentioned when we were executing DFS will be implicitly created by the recursive calls to the functions DFS in lowercase. So in the previous version of the pseudocode, the variable count was keeping the entry number, but when we executed by hand, we computed both the entry number, the time we invoked DFS on a vertex, and the exit number, the time when the vertex finished its DFS, when it came off the stack. So it's a very simple modification to incorporate this into our code. So what we do is that instead of having just a simple marked array, we have an entry number array and an exit number array in which we record the entry number and exit number for each vertex. So initially the entry number and exit number are 0 for everything, and the counters are also 0 for all these things. Now, as usual, we use entry count to determine whether something has been marked or not. So if the entry count is 0, then we invoke a DFS. When we enter the vertex, we increment the entry count and update the entry number for that vertex. Now for each neighbor, we check if it's been visited. If it has not been visited, we recursively visit it. And now when we have finished processing V, when all the edges outgoing from V have been considered, we will update the exit count and store the exit number. So a simple modification of the previous pseudocode allows us to actually keep track of both these numbers. So what is the complexity of DFS? The first observation is that DFS visits each vertex once. So there is an obvious order n factor to be considered. Now we have to see what happens when we actually visit each vertex, and this depends on the representation. So at each vertex, we have to examine all the neighbors. In an adjacency matrix, this means we have to scan the row for the vertex. That means we have to, regardless of how many neighbors it has, we have to spend order n time to pick up all the ones in that row. On the other hand, if we have an adjacency list, then we only have as many entries in the list as there are neighbors. So the amount of processing time for a given vertex is exactly the degree of that vertex. So overall, with an adjacency matrix representation, we have to do for each vertex, that is n times, we have to scan the row n times. So we have n squared as the overall complexity. On the adjacency list side, we have to scan each vertex once, so that's order n work. And if we add up the degrees across all the vertices, we'll get 2 times the number of edges because each edge will be examined at both endpoints. So we'll get something which is order n. So overall, the adjacency list representation gives us DFS in time O n plus m. So it's overall quite an efficient algorithm, but the exact efficiency depends on how you represent the graph. So it turns out that not only is DFS an extremely elegant way to explore a graph, DFS also provides us with a lot of useful structural information about the graph. We can directly read off some structural information from the DFS forest that we draw as we explore the vertices. So the first thing we can check is whether a vertex V is reachable from another vertex U. To do this, we start the DFS search at U, and if V appears in the tree that we generate starting at U, it means that V is reachable from U. If V does not appear in this tree, it means that V cannot be reached from U. More generally, if the graph is connected, then if we start at any vertex, the entire graph will be reachable from that vertex, so the forest will actually collapse to a single tree. So if the DFS forest is a single tree, it means that every vertex is reachable from every other vertex, and so the entire graph is a single connected component. And in this case, we note that actually the DFS tree that we generate is a spanning tree for this graph. We can also check if a graph is acyclic by looking for back edges. If there is a back edge in the DFS forest, it means that you can take the corresponding tree edges and then add the back edge and find a cycle in the original graph. And on the other hand, if there is a cycle in the original graph, if you follow the cycle up to the last vertex, then the last edge in the cycle must define a back edge. So the presence of a back edge indicates that a graph has a cycle, and the absence of back edges indicates that the graph is acyclic. Now we also computed these entry and exit numbers, the order in which we started processing and finished processing vertices. And it turns out that this numbering control contains a lot of very useful information of the graph. We just mentioned one example. We can use DFS numbering to identify what are called articulation points or cut vertices. Now a cut vertex is one which, if deleted, will actually disconnect the graph into multiple parts. For instance, in this graph that we have drawn here, if we delete this central vertex, then the edges around it will disconnect the remaining portions into separate components, even though the original graph is connected. So we can identify such cut vertices using DFS numbering. We won't describe the exact procedure, but it's important that such properties, which are slightly non-trivial properties, can actually be computed using this numbering. Now, one thing we should remember is that the DFS that we have described here is for undirected graphs. So in undirected graphs, we had exactly these two types of edges: tree edges and back edges. In directed graphs, the situation is more complicated. In a directed graph, the DFS forest may have not only tree edges and back edges, but also cross edges and forward edges. So we will look at DFS on a directed graph when we study the problem of topological sorting a little later in this section. So to summarize, DFS is a very simple recursive structure to systematically explore a graph. If we use an adjacency matrix representation, it takes order n squared time to do a DFS. But if we use an adjacency list representation, it takes time O n plus m. So for graphs with fewer edges, an adjacency list representation is more efficient. And the other important thing is that despite its very simple structure, DFS gives us a lot of information. So if we actually compute the DFS tree and also the DFS entry and exit numbers while we are executing the DFS, then we get a lot of useful structural information about the graph for free.